Let me start with something bizarre. In the year 1933, a mathematician named Carl Borsuk proved that at every moment there are two opposite points on the globe which have simultaneously the same temperature and the same air pressure, both for those points. It doesn't matter how chaotic the weather is, how turbulent it is, it's just a symmetry that is always there. It always persists. And here is another strange fact. Consider the wind. If you measure the wind direction at every point in the globe, you will find out that there's always a motionless spot, a point which is completely calm, like an eye in the storm. So here you can see that spot right there in the green arrow. You see that this is a point where some things happens around, but the point itself is motionless. And it's guaranteed, it's always the case. Those facts, by the way, this is called the hairy ball theorem. Some people like to think of it as a head full of hair from all directions, and there is just no perfect haircut. There is no way you can comb the hair in a way that doesn't produce any spots where the hair go all around. So, although it is presented here as something about the weather, in fact, both facts, they have nothing to do with the weather or with meteorology. They're even not really about the Earth. And it's not even about three-dimensional shapes. Those facts are just characteristics of round shapes or spheres. So the Borsuk result and the hairy ball theorem are part of a mathematical discipline called homotopy theory. So you might all be used to classical geometry where shapes are characterized by length, angles, circles, and precise and exact measurements. But homotopy theory is something different. It strips the shapes from all those details while retaining only the essence, what remains when the shape moves, stretches, and bends, as long as you don't glue or you don't tear it up. It is a much younger and obviously much less known field, but it somehow touches the much more deep aspects of the shape by ignoring all the fine details and remembering only those essence, the essence of the shape. It allows us to discover some basic core rules that govern the behavior of the shape, like the hairy ball theorem and the Borsuk's result. So imagine a bubble floating through the air. It flattens, it might stretches, it changes its shape, it inflates, but it never loses its essence, being a round sphere. So those aspects, those things you can say about the bubble that remain through the entire journey of the bubble through the air, that's homotopy theory. So my name is Shachar Carmeli. I am a new researcher at the math department of the Weizmann Institute, and I study homotopy theory, especially in high dimensions. So where the bubbles are allowed to float inside a very high dimensional space beyond our imagination. So to give you one more example of what that is about, for a homotopy theorist like me, donuts and your cup of coffee are considered just the same. That's because you can start to deform one of them and get into the other, the hole inside the donut becoming the handle of the cup. So when I look at this picture, I don't see the difference. So at the core of this area of research, there is something called the stable homotopy groups of spheres. Those are certain fingerprints or families of ways in which high-dimensional bubbles can twist and move inside very high-dimensional spaces. Uh, Here what you can see is a table of those stable homotopy groups, specifically how many there are in each dimension. And you see that the table already numerically is pretty interesting. There are some small numbers at the beginning, like 2 and 2, and then suddenly 24, 240, or 960 different ways in which bubbles can look inside a 15-dimensional space in this case. So this table is really at the core of what I study, and it contains a huge mixture of pattern and chaos. Humanity have computed this list of numbers roughly up to 90. So as you can see, for 100 and above, we just don't really know what there are. But already up to 90, we start to see things. There are those big numbers showing up or sudden jumps in complexity. While there are many other things we're not really able to completely explain. More than that, every entry in this table by itself encodes a huge amount of internal structure. So to give an example, let me focus on the first entry, the classification of one-dimensional bubbles in high-dimensional spaces. And already this entry contains this picture. This is called the Hopf vibration. That's a collection of circles or wide-dimensional bubbles floating inside three-dimensional space, and there is something very special about the way they are organized. Those circles cover the entire space. It fills the whole three-dimensional space, but every two circles are connected. They are all linked. No two circles in this picture are far apart and can be separated. So just imagine if that picture is what's in the first entry, what there is in the others. Those are pictures of high dimension we cannot even imagine, and they are all very beautiful like that. Okay, that's all. Might sound very abstract, and well, it is very abstract. And a natural question again is, how is it connected to our real life? But it turns out that homotopy theory shows up, and it shows up in surprising places and in surprising ways. So it's related to robotics, it's connected to string theory in physics, to condensed matter physics, and also to the analysis of big data. Let me focus on the robotics example. So imagine you are trying to program a robotic arm moving from point A to point B, trying to avoid all sort of obstacles along the way. So every position of the robotic arm can be regarded as a point in a high-dimensional space called the configuration space. And this space, for appropriate choice of obstacles and robotic arm, can be pretty complicated. It can have twists in it, it can have holes inside. And therefore, it can be analyzed using homotopy theory. Specifically, homotopy theory helps us understand, for example, if it's even possible to get from point A to point B, and if so, how complicated a method to do it should be. Specifically, it is used to show that in many cases, strategies of motion necessarily have so-called unstable points, points where the strategy have to be drastically changed to finish the task. And those are like the eyes of the storm in the robotic situation. Those are those points where something strange is happening, like in the Hairy-Ball theorem. That's all really nice, but that's not really the reason I do homotopy theory. I'm not here to construct a better robot. To be honest, I do homotopy theory just because of pure curiosity. It's like a new unmapped world, like discovering a new mathematical continent within the entries of this table. And I try to understand it, to understand this table and how it behaves, how fast the numbers are growing, what makes those sudden appearances of complexity appear, and what is the real structure underneath. I don't know what resources are out there or how next generations are going to use it. But I know this is so rich and full of potential that something must come up in the end. Or, as said the great mathematician of the 19th century, Henri Poincaré, by the way, one of the founders of the field, the mathematician does not study pure mathematics because it is useful. He studies it because he delights in it. And he delights in it because it is beautiful. I find homotopy theory incredibly beautiful. It exemplifies that even the simplest things, like bubbles floating through the air, contain secrets waiting to be revealed. Thank you very much.
Yeah.